Hello. Welcome to our webinar. I'm really sorry we are late in starting this. We have had technical difficulties. Alexander is joining us today from PCS and has a wonderful presentation. So I'll just do a very quick welcome to the IMechE Tribology Group Committee webinars aimed at our early career researchers in this area. Alexander MacLaren has joined us from PCS, as I say, and he will be talking to us about electric vehicles today. Alex, I can't see your slides at the moment.
Yeah, let me just share them. Thank you so much, Kate.
I will hand straight over to you to save us being any later in starting. Thank you. Final point from me. If you do have any questions, please put them in the Q&A chat and we will get to them after Alexander's presentation. Thank you.
Awesome, thank you. Let's get started. My apologies, we were backstage and merrily giving the presentation, which is of course not what you guys need in the actual webinar. So I'm Alexander MacLaren. I'm going to talk about what the future might hold for electric vehicle transmission lubrication. I'm going to focus on gearbox tribology in electric vehicles. I'm going to talk about what sets EVs apart, what some of the problems that we might experience are, and indeed have been experiencing for the last decade or so, in terms of the way that we formulate lubricants and the way we design transmissions. And then I'm going to look at potential solutions, what the future might hold in this space. But first, just a little bit about me. So I'm Alexander MacLaren. I did my undergrad in mechanical engineering at Imperial College London, during which time I looked like this. I had excellent fashion sense, but I should stress that we were made to wear those. And then I did my PhD in the tribology group, also at Imperial, in the efficiency and reliability of electric car transmissions. And I also spent some time in cardboard boxes. I then got a grip and I cut my hair, and I am now a research and development engineer and tribologist at PCS Instruments. Let's start at the beginning. So actually, EVs have really quite a long history. There was a Scottish inventor in the early 1830s who put an electric motor in a carriage. And this thing, it had galvanic batteries which weren't rechargeable. So it could go for, maybe a couple of minutes, and it could maybe only go at a couple of miles an hour before the batteries petered out and needed replacing. But technology improved during the 1800s. And so by the turn of the 20th century, electric vehicles were actually quite popular. They held the land speed record. And there was this dude whose name you might know called Ferdinand Porsche, who in 1898 designed this electric vehicle. Porsche's first car was electric. He worked at this time for the Lohner company, and he had a talent, it seems, for mechanical engineering. And so he designed this really quite complicated transmission that had 12 gears, some of which were for reverse and some of which were for braking. I think 6 of them were for going forward. And I've got no idea how it worked. So if you know, please do let me know. I'd be fascinated. But at the turn of the 20th century, EVs ruled the roost. There were many, many different designs, and to understand why we might want to design a transmission in a certain way, it's worth just first looking at what different types of transmission there are. So firstly, we have direct drive, where you connect the motor directly to the wheels via some coupling. And obviously, we want to go at several different speeds in a land vehicle. So when you have direct drive, you have to work out a way of making sure that the motor can operate at several speeds. And in this pre-semiconductor era, it was necessary to devise a relatively complex system of electrical circuits such that the motor could be energized, at different frequencies. And so there were some EVs that operated on that principle. There were also belt drive EVs, so leather belts, I think, obviously think turn of the Industrial Revolution, and then slightly more torque-dense design, chain drives, think motorbike transmission. So these were all represented in early EVs. But of course, if you want more power density and more efficiency and potentially a higher reliability, what you need is a geared transmission. So we might have a single-stage reducer gearbox like this, so spare or helical gears, or we might have a two-stage, still single speed, but two-stage reducer. And in fact, if you make these helical gears, this is what we see in the vast majority of EVs on the road in 2025. There are other architectures, of course. So, for instance, this epicyclic gearbox is brilliant because epicyclic gearboxes provide really quite high reduction ratios, really quite power dense, and they are coincident axis, so inline drive, which can be useful from a design perspective as well, keeping things small and light. But they're a little bit more expensive and a little bit harder to manufacture. To understand which transmission we might choose, it's then necessary to zoom out a bit and look at the whole architecture of the vehicle. So here is our familiar internal combustion engine car. It's got a fuel tank, it's got an engine, and it's got a gearbox. And the power flow to the wheels follows that single path. Then people said, well, it would be good if we had an electric motor in a car. And so here is a hybrid electric vehicle. We now have the same flow path from the power flow path, tank, engine, gearbox, wheels. But now we also have a battery, a power inverter, and a motor. And so the gearbox has to be able to draw power from either of those sources. It may also be possible to reverse the flow of power to the battery using the engine to charge the battery. And the motor and the generator might be the same electrical machine, or they might not. A plug-in hybrid is very similar. It's just that it probably has a slightly bigger battery and it can accept charge from an EV charger. And so it will definitely be able to power the wheels with an electric motor, and it will definitely be able to power the wheels with the engine, but there might not be a direct link between the engine and the wheels. The link might be electrical via a generator and then a motor. And in this case, the two electrical machines have to be separate. There's then a range extender, which just breaks that link completely. And so we have an engine whose job is mainly to charge the battery such that we can then use a motor to power the wheels. And actually, this configuration might increase the efficiency of the engine quite significantly, because the engine can run at constant speed where it's happiest, and then the electrical transmission can do the speed and torque shift. And then we have a much simpler case with the battery electric vehicle, where we have a big battery, power inverter, motor, gearbox. So this is what people think of as an electric vehicle, but it's worth also not excluding the hydrogen fuel cell electric vehicle. So now, instead of relying solely on the battery, we might have a little battery to do a bit of load smoothing, but ultimately most of the power comes from a hydrogen fuel cell in real time, and we have a hydrogen tank, of course. Apart from the internal combustion engine vehicle, all of these vehicles are electric, in that at some point they can be powered only by an electric motor. And so in terms of what I'm going to say today about transmissions, all of these are of relevance. Let's just look at some of the characteristics you might need to study in order to design the transmission. Here is a Fiat 500. It has an engine. And if we look at the torque speed curve of the engine, we see that the engine can provide torque over a relatively narrow speed range, between about 1,000 and about 6,000 RPM. Let's say that the slowest speed that you could wish to achieve in your car was about 5 miles an hour, crawling around the Tesco car park, for instance. The dynamic range of this prime mover is only 1,000 to 6,000. And so we would get up to, if we really floored it, about 30 miles an hour in that car, which could go at 5 miles an hour in the slowest, if we had a single speed. That is why we need several gears in a car, so that we can get up to motorway speeds. 30 miles an hour would be very inconvenient on the motorway. We also notice that the maximum power point happens at a very specific speed. So we have torque on the light blue curve and power on the dark blue one. Let's now look at an equivalent electric vehicle. So this is a Fiat 500e. It has a very similar bodywork to the Fiat 500, but it's an EV. I've made some simplifying assumptions in deriving these curves, and my source is down here, by the way, but the torque curve of this motor is very different to the torque curve of the engine. It has this constant power point, and then, this constant torque line here, and then it has this constant power bit here. It's also worth noticing that the engine can't go any slower than its minimum speed, about 1000 RPM, otherwise it will stall. Whereas the motor can provide torque down to 0 speed, which is very useful. So I said that we'd need lots of gears in the ICE car, and here they are. Obviously, if you have a gear ratio that is a reducer, it divides the speed and it multiplies the torque. So here are the 5 gears, scaling that torque curve in those 2 ways. Here's the EV. It also has a gearbox, but it only has a single speed, and so I've scaled it appropriately. What we see, and by the way, here's the imaginary direct drive situation where we have the engine directly driving the wheels or the motor directly driving the wheels. We can see neither of these would work particularly well. And in the internal combustion engine car, our minimum speed would be about 70 miles an hour, which would mean we'd have quite a lot of clutch slip as we tried to accelerate to that speed. And indeed, the car might not be too fun to drive. We have this constant torque bit here and this constant power bit here. And it turns out that when we implement our change gearbox in the internal combustion engine, we achieve a relatively similar torque speed profile. This is kind of what all internal combustion engine cars are capable of. And here we have it in the EV for free with only 1 gear. This is a convenience of having an electric motor. You can do this without the change gearbox. So that is why most electric vehicles only have a single speed, and they're considered an automatic, but that does a cruel injustice to the amazing piece of technology that is the automatic transmission, because of course an electric vehicle doesn't have an automatic transmission. It's just the motor is just better for the job. So a transmission design requires understanding of certain performance requirements, and the big one, of course, is that it can supply the torque, or it can transmit the torque that the motor can supply at very low speeds. We saw that stall condition. We're tribologists, so let's look at the concomitant lubricant requirements. We need EP performance so that we reduce wear and reduce the potential for scuffing at those very low speeds at very high pressures. And we also need sufficient oil viscosity to generate enough elastohydrodynamic film in our gear contacts and our bearing contacts that under high pressure, at relatively low speeds, we're not still in boundary lubrication. And so as the sliding speeds increase when we accelerate, we don't end up damaging those surfaces. We also need to operate over a pretty wide speed input range, or input speed range, sorry. And so the lubricant has to be shear stable, and it also has to not foam. The fluid is often required to cool not just the gearbox, but also the electric motor, which is often, in close proximity. And so it might be required to be flowing over copper windings, and it also will be required to have good heat transfer properties. This is where it starts getting tricky. If you are exposing the gearbox lubricant to copper, chances are it's going to have a lot of sulfur-containing EP additives. And so recent EV designs have been having to make a tricky trade-off between sulfur and copper compatibility. And of course, that means that lubricant formulators have a relatively difficult task, which varies depending on the gearbox design of the manufacturer. We also, if we just think about what is required for heat transfer, it's a flow, and so we can solve the energy equation for that flow, and we find via the advective term there is a coupling to velocity, and that couples it to the momentum equation. And of course, the diffusion coefficient in the momentum equation, so that's just Navier-Stokes, is viscosity. We find that as viscosity decreases, we get better heat transfer. And of course, if we can decrease viscosity enough that we can trip the flow to turbulence, then we get better mixing and better heat transfer still. So this creates a conflict between heat transfer properties, which require low viscosity, and surface damage requirements that require higher viscosity. So you've got to make a trade-off there too. These tend to be fill for life applications. So as well as shear stability, we also have to have sufficient additive treat rate that additives don't get depleted. And of course, the thing goes jolly fast. So we have to have good high cycle fatigue performance. So that's macro and micro pitting, and also wear resistance over life. And finally, the motor, the electric motor, is a very efficient machine, particularly compared to an engine. So we might get 80, 90%, possibly greater than 90% electrical efficiency in the motor. That shines a brighter light on the gearbox in terms of where we might be wasting energy, and where we might improve efficiency. And of course, consumer range anxiety is one of the big market blockers to uptake of EVs, and because people are scared they won't be able to drive far enough without their EV needing recharging. And so ultimately, the more efficient the gearbox, the further the range of the vehicle with no other modifications to the vehicle in terms of its cost or weight. But the lubricant properties that affect efficiency are relatively complex and diverse. And indeed, this was the subject of my PhD thesis. So we're going to have a look at those in a minute. But first, let's look at some solutions for formulation, and some things that we might need to achieve in the present and in years to come. So ultimately, fluid formulation requires making trade-offs based on data, and that data can come from experiments or it can come from models validated by experiments. But in both cases, the tasks we have ahead of us are evaluate the impact of fluid rheology, both on friction and on fluid losses. We need to resolve the thermal coupling in the gearbox. So that is, as your oil heats, it changes the friction properties, that changes the amount of heat generated. And also, of course, if we have thermal management going on, heat there's a source of heat elsewhere. And you might even, there are some people who think it would be a good idea to try and cool the battery directly with transmission oil. I'm not sure I'm in that camp, but it's been suggested. I also recognize the diversity of gearbox architectures on the market right now and surely in the future. And I know of no robust, peer-reviewed, publicly available comparison, that considers the variables we might want to control between even two different gearbox architectures in terms of efficiency or reliability, particularly under EV relevant conditions. And it's complicated because architecture is a very multidimensional thing. But we might at least, design a two-speed helical reducer and then design an equivalent planetary gearbox with similar specifications and see under equivalent oil fill level or whatever, which is more efficient. I don't know of any work that has done that. And if you do, please get in touch. But that's something that I'd love to see. And also assess and mitigate surface damage. Now, of course, we've studied surface damage for many, many decades, and it's very complex. There are all these very exciting phenomena that can happen, and they compete with each other, and they happen under different conditions. But as we change the requirements of gearboxes, particularly in EVs, where we want to get to very high speeds and very high torques and very high efficiencies at the same time, we periodically have to re-examine the mechanisms underlying those phenomena. So ultimately, what we need to do is make the link between fluid formulation and simultaneously efficiency and reliability. And that was the basis behind the proposal that got the funding for my PhD project. You have to look at efficiency and reliability in tandem, because if you optimize one at the expense of the other, the gearbox is useless. There's active research on all of this. And so let's look at some of the inroads that have been made into these problems recently. And there's going to be a heavy bias in the next few slides towards work that I personally have done, but I'm also going to talk about some of the space more broadly. These things that are in bold are big, complex problems. So fluid rheology has sparked a transatlantic debate of some proportions in the last couple of decades. Thermal coupling is very computationally expensive to study and very difficult if you model it, and obviously very difficult to measure. Architecture is hugely high dimensional, and surface damage is time dependent and extremely complex, multi-length scale, multi-physics problem. So let's break it down. Let's start with efficiency and look at the phenomena that cause losses. Efficiency is defined as power out over power in. And of course, the difference between those two variables is loss. So we want to know the sources of power loss in our transmission. We might have friction losses, which result from rolling sliding contacts. And of course, the lubrication regime here tends to be EHL or boundary EHL. And so we have EHD friction loss in those contacts, and that can dominate the losses in the transmission. Equally, we have fluid losses, which are considered energy lost by shearing of the lubricant outside the contact. And as we spin up the gearbox, actually a relatively complex series of energy dissipation mechanisms, which effectively are characterized by the transfer of energy from the gear to viscous and inertial energies in the fluid. And we have windage, which is the interaction of gases with the gears, and drag, which is the interaction of liquids with the gears. And then we have various pumping, trapping, and pocketing phenomena, which arise in different situations, and the terms are sometimes used interchangeably. But this is a complex, multi-phase, time-dependent flow that requires some study. Both of these phenomena are high-dimensional, and they're very difficult to predict. This woman is the legend, Dame Maggie Adrian-Pocock. She visited the lab at Imperial earlier this month, and she is sitting next to a rig that I spent many, many hours in front of. This is the HD High Speed, and this was the one that I helped develop during my PhD. And ultimately, it is one of a whole suite of new test methods that will be required to characterize lubricants, to understand performance of transmissions, and ultimately to answer some of those questions that I listed earlier. So the thing that I did with this rig was use it to measure film thickness in an EHD contact at the same time as I was measuring friction, and to characterize the behavior of those contacts. The rig is amazing. It uses this white light interferometry technique where we force the lubricant film, which is in this gap here, to introduce a path difference between two beams of white light. And then we recombine those two beams, and that results in a colored interferogram. And so we can determine film thickness from those colors. The rig then actually puts that interferogram through a spectrometer, which means it can measure film thickness to nanometer resolution. But I also modified the rig to measure friction at the same time. So this four-dimensional plot here, on the z-axis, there's a key up here. On the z-axis is friction coefficient. On the x-axis, there is entrainment speed, and on the y-axis, there's sidewall ratio. So if you look from the right-hand side, you can just see a series of traction curves at various different entrainment speeds. If you look from the left-hand side, you can see a series of Strybeck curves at different sidewall ratios. And then the colors are derived from the central film color. I've just sampled a little box in the middle of each image of the interferogram. And you can therefore see film thickness changing at the same time as you see traction changing. Now, the behavior of these traction maps was quite surprising at high speeds. I believe this was the first attempt to measure traction up to 20 meters a second. And I believe that soon there will be the capability to measure traction at speeds higher than that. So this is an exciting space for EV designers because they're able to access this thermal EHL regime where things behave quite differently. Here is a steel on sapphire contact. So, in terms of contact pressure, quite similar. This is 1.3, I think, gigapascals, 1.4 of maximum hertz pressure. And we find that at high speeds, the traction curve does something very odd. We also find that at high sliding speeds, there's not much difference between these three temperatures, 20, 60, and 100, which means that there's no viscosity dependence in the traction, which is, in direct contravention of what we might understand isothermally with classical EHL. And so these are important findings for trying to optimize efficiency at high speeds in electric vehicle transmissions. You also might say, well, that's all very well, Alexander, but how do we know that that corresponds to real life? Well, one way of being more convincing on that front is to get an actual EV transmission. So here's the transmission from a 2016 Tesla Model S all-wheel drive. This is the rear axle drive unit. And what I did, this was thanks to the wonderful people at the Ashland lab who work at Valvoline. This was in the States. I went for 8 weeks and I visited them and I did these tests on this very scary rig. but this allowed me to actually circulate power. So these dynos act as the wheels on the car, and they absorb power from the drive unit, and then there's a battery simulator that allows me to power it. And in this way, I was able to measure efficiency maps of the drive unit. So here's motoring, and here's absorbing. And so absorbing is negative torque. And we find that although, at very high torques, we have quite high efficiency, actually the car tends to operate down here. So often our efficiency is, between 70 and 90%, which is much lower than most models would claim. And this kind of makes sense because there are several phenomena that perhaps those models aren't resolving, not least the energy dissipated by fluid losses. I was also able to put the thing through an actual drive cycle. And if you want to know more about this, I will refer you to the relevant chapter in my PhD thesis, which, shows the details behind this work. But this is the sort of thing that OEMs are doing. They're doing it much better than I did because they've got whole teams of people working on it for longer than 8 weeks. And these tests are very expensive. They don't give you all that much information because, of course, efficiency depends on many, many things, and you're not measuring any of those things. You're just measuring efficiency, and hopefully you're controlling temperature and various other things. But in terms of understanding the performance of a certain architecture, this is probably the way to go. In terms of resolving and understanding phenomena on the microscale, this is definitely not the way to go. And we need to do both. One interesting piece of work, which I respect very highly, is from a colleague of mine, Joseph Shaw, at Imperial, and he built a model that effectively does this test, but in a computer. And it uses various elastohydrodynamic traction models and the best churning models that he could find, and then he made better ones during his PhD based on measurements that he did himself at very high speeds. And he has modeled the efficiency of actually a gearbox very similar to this, possibly actually even this gearbox and then some other gearboxes as well. And then he's changed the fluid properties, so you can effectively just change the oil in his model gearbox, at the drop of a hat, and compared the effect of the rheology on efficiency in those transmissions. So I would definitely recommend reading this paper and any of Joe's other work. One other thing you could do is modify the gearbox itself to try and measure certain properties about it. So in this study, I was looking at churning loss, which is the energy lost because you splash oil around inside the gearbox. This is a very similar transmission to the one on the previous slide. It's the front axle drive unit from the same car. And here we see that classic single speed, two-stage helical reducer. The motor is attached to this thing with a bearing on it, and there's a gear behind that bearing. What I did is I put this transmission in a rig that I built. And so I spun it up with an external motor, and then I used an inertia rundown method to measure churning torque. Now, if there are any clued up people in the audience who are thinking, oh, inertia rundown is a transient technique, surely you're measuring churning torque in under transient conditions, and that won't agree with steady state conditions, I would point you to my thesis, which compares both and finds that actually inertia rundown compares relatively well with steady state measurements. So although I know some people are opinionated on this issue, actually I'm relatively confident that these results would reproduce. One very interesting thing I found was I was able to temperature control the gearbox, so I measured the effect of viscosity, which is a hot topic because people are trying to work out what viscosity to formulate the transmission fluids to. And so I did this at 4 speeds, that's these 4 lines, and I changed the temperature in the gearbox. So this is a sort of 5.4 centistoke automatic transmission fluid. If it were a bit more viscous, it would probably conform to Dextron 6. In fact, it might conform to Dextron 6 anyway. And yeah, I think it does. The operating temperature range of the vehicle would put it in roughly these viscosities. So we see that, as the fluid gets more viscous, we do have an increase in churning loss. But I then put a different, much, much more viscous fluid in the transmission, allowing me to look at higher viscosities. And this is what happened. So what we see here is, and actually there's another paper by Joe on this topic as well, once you get to a certain viscosity, the reflow time in the gearbox means that the fluid stays out the way for longer. It doesn't flow back and then impinge upon the gear again. And so churning torque goes down as you increase viscosity. And then it comes back up again as the fluid becomes very viscous indeed. This is quite interesting because it contravenes conventional wisdom. As you increase viscosity, you will increase churning loss. Well, no, not necessarily. And look at this. This is lower than any churning torque that you might see in the operating temperature range, apart from maybe at quite high temperature. And so what if we were to try and optimize for this condition instead of this one where we get really quite aggressive surface damage? Just a thought. It's not necessarily the right solution, but it's worth knowing. The other thing that I looked at was the effect of speed and the effect of fill volume. So here are two sets of measurements that I did at all these viscosities, one at full fill, which is about 2 liters of oil, and one at half fill. And you see at low speeds, there's a bit of separation. And then this is at much faster speed. So with this car, this would be 88 miles per hour, just an arbitrary number. And we see that actually, I mean, look at this viscosity variation. The effect of viscosity is much, much weaker than the effect of speed and the effect of fill volume. So that's interesting because it means that the design of the transmission, the design of the motor, the gearbox architecture, and how much oil you decide to put in it have a very big effect compared to the viscosity you end up choosing. And of course, if you're going to put loads of oil in your gearbox to try and make it cool the motor, that's worth knowing. It affects efficiency. Now, I studied here a single speed two-stage helical reducer. There are other architectures. And as I said earlier, the vast majority, I like that. But here are some alternatives. So in the Porsche Taycan, we have a two-speed helical reducer. And so there is this clutch pack, which allows us to switch between two different speeds. There's no coincidence, actually, that this is effectively a dual clutch transmission. So dual clutch transmissions are something that Porsche love because they're like automatics, but they switch faster because you have two different shafts. And on both lay shafts, this transmission effectively just only has one speed, whereas in a 6-speed DCT or a 7-speed DCT, you might have 3 or 4 speeds on each lay shaft. But other than that, it's pretty much just like Porsche's DCT, which maybe makes that connection. And there is some argument for doing this because then you can optimize for very high speed if you want that, and then very high torque if you want that. So you might have a speed gear and a torque gear effectively. But for most EVs, manufacturers consider this unnecessary. You also have this eCVT thing in the Toyota Prius, which is amazing, but it allows it to perform the power slip between the engine and the gearbox, the engine and the motor, sorry. And then you also have an epicyclic gearbox in the Lucid Air, so there are other options. I'm going to just take a brief foray into surface damage, which is another thing that we need to study because it's complex. It depends on a particularly inconvenient variable, and that is time. But there are many established test methods. So future test methods might use for instance, this triple disc rig, which allows you to generate micropitting at 1 million cycles per hour or upwards thereof, perhaps in the future. And you might also study wear or scuffing or tribofilm development or electrically induced damage on a ball on disc rig. Both of these rigs were designed to be maximally application relevant, so to closely mimic rolling sliding contacts in gears and bearings. And it's important that the tests are relevant to the application. There are so many tests. So for instance, my pet hate is the 4-ball wear test because it just doesn't represent the 4-ball EP test, I should say. It doesn't represent the application that it's really designed to. EP in gears is very different to EP in pure sliding under extremely high contact pressure and very smooth specimens. It's just, scuffing is complex. Micropitting is something that is potentially a problem at very, very high cycle conditions. And this was some work unpublished that I did during my PhD, comparing several formulations. So we see that the base fluids don't really provide very significant micropitting under these very aggressive conditions in this accelerated test above about 10 million cycles. Or until about 10 million cycles. Whereas the gear on the ATF, because they have anti-wear additives in them, actually are really quite deleterious from a micropitting perspective. Now, of course, this ATF is used in EVs in such a way that it probably isn't a massive micropitting risk. But under these conditions, you can see that at higher cycle or at higher contact pressure in the future, we might need to reformulate these fluids. Scuffing is another exciting one. So this is one of the names given to this very catastrophic adhesive wear that we get when the film collapses for some reason. We also call it the scoring, and it happens on gears. Quite why the film collapses, there is a lot of debate about in the literature, and we don't really know, I would say. There have been many theories, and none of them explain all the data. Perhaps several of them, compete or collaborate. And we know what happens after the film collapses, but in terms of studying it, I think there's more work to do here. This was some work that I did during my PhD, again, unpublished, after a method that was published by Peng. So I used the contra-rotation conditions here. So the ball is going in the opposite direction to the disc. The sliding and entrainment speeds are still in the same direction, but now the sliding speed is greater than the entrainment speed. I set the lambda value to 0.8. So here we're in mixed lubrication, and we saw that these three fluids that I studied, which were a gear oil, an ATF, and then PaO5 with a little bit of ZDDP, actually quite a lot of ZDDP in it, just as a reference, we find that they don't scuff at the sort of loads that you might expect under gear contacts in EVs. But if you ramp that up to 2 gigapascals, it's a very ambitious load or pressure, sorry, for an EV gearbox, but I have heard it suggested. We see that there is scuffing really quite early at really quite low sliding speeds under these test conditions. And obviously this is an offline test. This thing isn't a gearbox, but it allows us to perform much more repeatable and much more useful scuffing tests that are reasonably cheap. And gear scuffing tests, again, are famously not cheap and not necessarily repeatable. So future test methods in that area. And I'd also just like to highlight some brilliant work by a colleague at Imperial, Ahmad Yusuf, which was published 2 weeks ago. This is on electrically induced damage. He used the MTMEC to do this. And he found that, so this is the slim images from his tests on a commercial ATF. Non-electrified, they look like this, which is sort of, believable. And then as he's set the ball to be the cathode, we see a change in film forming, and the anode, we see a very significant change in film forming. So he's actually tribologically activating various additives and changing various wear mechanisms here by applying a small voltage and a very small current. And many people using this rig are applying much, much larger currents. But I think this paper is possibly something to aspire to in terms of understanding these mechanisms. Definitely a good read. It's open access. So where next? My animations have let me down. I think that in the coming years, we have a discussion to have about viscosity. People trying to push it extremely low, sometimes 2.5 centistokes, maybe lower at 100 C. And I don't necessarily think that there is a good case for that being the answer, certainly in terms of optimizing efficiency and reliability in tandem. We also have to look at sulfur-containing anti-wear additives. In terms of architecture, there are amazing things on the horizon. This in-motive transmission by a company in Canada called InGear has recently had significant investment from Suzuki. It's effectively just a chain drive with a small sprocket and then a larger sprocket, which is split into sections, and it can translate axially, so it can then piecewise take up the chain. So you have a two-speed transmission like this. And of course, it's not a chain and it's not sprockets, because these look like involute gear teeth. But this is touted as the sort of next generation in the EV architecture. Who knows whether it will happen? And then I also saw a paper recently about pericyclic gearing. This is actually relatively new by gearing standards. It's, we've had pericyclic gears for about 30 years, to my knowledge, and they're very, very torque dense, and therefore potentially extremely good for high power, compact, high reduction ratios. And so I've heard it said in peer-reviewed papers that you might have one of these in a next generation heavy goods vehicle, for instance, like in electric lorries. Of course, If we could change the motor design, so that thing about having to have quite a small motor that goes very fast and then reduce the speed such that the vehicle can travel at the speeds you want, if we could change that, maybe by moving from radial flux to axial flux electrical machines, we might just be able to have direct drive again and do away with the gearbox altogether and have very high efficiency mechanical power transmission. But that would require axial flux machines to be able to be scaled up and to be sufficiently cheap. And neither of those things are currently true. And finally, of course, the gearbox has to be integrated into the rest of the vehicle. How does it talk to the coolant for the battery? Does it, is the lubricant also the coolant? How does it communicate with the inverter and the motor, and in terms of thermally and mechanically and electrically even? So these are the things that I'm excited to see what we come up with in the next few years, and that will continue to challenge tribologists worldwide in this space. With that, thank you so much for your attention, and please do let me know if you have questions.
Thank you so much, Alexander, for that fascinating talk. I love how you've started with giving us a little bit of history and taking us all through. Certainly learned a lot myself from that. If you do have any questions, please pop them in the Q&A. We have a few minutes where we can answer these now. I'm going to start with a question to you, Alexander. So you mentioned range anxiety, and that's sort of aware of EVs being very different in summer and winter, or quite different in summer and winter, to the range that you can get. Do you think tribology actually holds the answer to that? And do you think we're far off being able to make it more comparable year round?
Oh, that's such a good question. I nearly started by saying, the elephant in the room with EVs is, of course, that the central issue is power storage. It's always been power storage. And the reason that they were outcompeted in the 1920s by internal combustion engines is that the fuel was more power dense for internal combustion engines. Of course, we didn't have lithium ion until the 70s. And so now we have batteries, and they're heavy, but they work. They're also temperature dependent. And of course, that's a tricky problem. Some of it is tribology in terms of the way the battery is designed, and surface interactions, anode, cathode, electrode. It's a complicated branch of mechanical engineering and obviously chemistry that I am not really involved in, so I struggle to speak to. But certainly in terms of battery cooling, which is a massive field, or maybe battery temperature conditioning. If it's very cold, we might be able to improve the range by heating the battery a bit. And there are designs that do that. That has to be integrated with the tribological concerns of, if we're using a transmission oil to move heat from the motor, as the Tesla does actually, moves heat from the motor to the battery coolant and then into the battery to condition it, then that all affects range. And the design of the system, the software that does that, all has an effect on the range of the vehicle, and that it happens via tribology. So certainly tribologists in the team that designs that product have a role to play.
Lovely. Thank you very much. We've got some more questions coming in. We've got a question that says, thanks, Alex, for the great talk. In the churning loss study, how did you eliminate other sources of loss, such as thermal loss or shearing, to end up measuring only the churning loss?
Brilliant question. Thermal loss, I don't think is a well-defined term, because, of course, temperature alone doesn't cause loss. But certainly, thermal conditions of the gearbox change the losses. Most of the losses come from some form of shearing. So either we're shearing air, or we're shearing oil, or potentially we're shearing steel. We might also be shearing grease in the bearings. And so I did tests during my PhD with unsealed bearings and oil lubricated ones, and then sealed bearings, grease lubricated. And you do see a difference. The problem with the inertial rundown method, well, actually, one of the advantages of the inertial rundown method compared to steady state is that it happens very quickly. So you you minimize the effect of any temperature transients. But the problem with the inertial rundown method is if there is any temperature transients, then you will capture that in your losses. But I speak to that issue in my thesis in great detail, so I'll refer you to that. And equally, I think the simple answer to your question is I did a measurement with oil and I did a measurement without oil. So obviously the flow is a little bit coupled, but the windage is much less significant in magnitude than the churning. So we kind of isolate the effect of oil by doing that, at least to a first approximation. And that is what allowed me to make the conclusions that I made.
Lovely. Thank you very much. The next question again, thank you, Alexander, for the great presentation. Did you come across a relation between tractive behaviour and pitting damage during your studies?
Oh, there are many papers on this. I would refer you to Benjamin Wainwright and Mao Ueda from Imperial and many others, which look at the effect of friction on micropitting. So obviously, high cycle fatigue, which is I think what's being mentioned, Kate.
Tractive behaviour and pitting damage.
Yeah, pitting damage. Cool. So those are stress activated mechanisms. Ultimately, you have to have a shear stress to drive them and to drive crack propagation. And the shear stress comes from friction. So yes, there is a correlation between tractive behavior and pitting or micropitting, indeed, depending on whether your stress, whether your crack geometry is driven by asperity stresses or driven by macroscopic stresses like inclusion or something else. I didn't really look specifically at that effect in my studies, but my thesis also refers to quite a lot of people who did, so worth looking at those.
Okay, well, a related question, do PAOs perform better in terms of pitting reduction? Is this due to lower limiting shear stress coefficient?
Complex question, because often to get high enough stresses, yeah, you might simplistically say, okay, yeah, PAOs have lower traction coefficients because their high pressure rheology is different to other base oils, and so they provide less friction, and therefore they are likely to lead to longer pitting life. But I wouldn't say that with confidence, and I haven't studied it myself. I didn't do any work on pitting, particularly because there might be other issues at play, like what happens early on in the test. How does the roughness evolve during, or how does the surface evolve during the life of the component? And also, is there crack pressurization going on? How does the lubricant work to damp vibrations? All of that sort of thing. So it is quite multifaceted.
Lovely, thank you. Next question relating to industry. I was wondering if you had any insight on whether OEMs are starting to select viscosities for their transmissions in the medium viscosity but low churning losses range. Has the research trickled down to industry yet?
Oh, this is such a good question. Thank you for this. So my take on this is that OEMs are driving extremely low viscosities, and formulators are struggling to meet their requirements, possibly because those viscosities weren't a good idea in the first place. But that's just my opinion. I obviously have pointed out in the talk that the way that you design the gearbox, so just literally the shape of the gearbox casing, what your clearances are, whether you have ribs in it, how the flow will behave, how much oil you put in it, all of those things affect the way that viscosity modulates churning loss. So there is no churning loss optimal oil because it's the gearbox that does the churning. And viscosity is just one thing. And actually, there's lots of very interesting work from the French group Le Prince and Churning and Vellex over several decades who have looked at the effect of many other variables like gear geometry and even surface wetting properties, so like surface tension and liquid gas solubility, and the way that the oil takes on air and foams obviously also affects churning. So it's actually also quite high dimensional, and I wonder if we're looking at it in a slightly too simplistic way sometimes by saying, oh, this is a medium viscosity fluid and it's low churning loss. Well, what does that mean? It's actually about the gearbox.
That's lovely. Thank you. I think we've got time for one last question. We actually have a hand raised. Gerald, would you like to talk? I should be able to pop you on. Now you should be able to unmute yourself if you'd like to. Is there a hand raised accidentally?
Can you hear me?
Yes,
Yeah.
we can.
Okay. Yeah, no, nice presentation, Alexander. It's really good to see you digging into this area. The question I put was that I've worked in the bearing industry for 39 years. I recently retired a couple of years ago, and we found a very strong relationship, a strong synergy between bearings and gears, and lubrication is a key aspect for both. And over the years, I found that there's a lot of material science that comes into it for surface hardness, fatigue resistance, scuffing wear, these sort of things, additives in the lubricants, all sorts of things that come into play. And so we were really working on reliability engineering of industrial machinery, and lubrication was a key aspect to that. I just thought, have you got any thoughts on those aspects of materials science and heat treatment and those sort of things for the future, because that can also strongly influence the outcomes?
Absolutely. I worked next door to some nuclear materials scientists during my PhD. Sorry, Gerald, did you have anything else to say?
No,
Did I cut you off?
No,
okay,
carry
cool.
on.
And one of the things these material scientists used to say was, steels are absolutely amazing. We come on leaps and bounds every year in terms of what they're capable of. But my understanding is that we've used reasonably or relatively consistent, at least bearing steel test specimens in offline tests for the last few decades. So perhaps there is material science to do, but to be honest, I am not a material scientist, and neither am I a lubricant chemist. And so although I can say, yes, excellent, there will be work to do and we'll make these things better, I actually don't know how far we could go, or what that would involve, or whether it's reasonable to expect that to happen. Certainly, metallurgical solutions to gear wear and to gear damage are also application dependent. And of course, we see lots of coating technology and
Yes.
of various different types going into the space. But in a very cost sensitive application, like mass manufacture passenger cars, I'm not sure whether that would certainly, if you could change the material, the bulk material, and have it heat treated in a way that was cheap to do, that would be amazing. If you wanted to put DLC on every electric vehicle gear, that might not be quite so plausible. So yeah, what I'm really saying is I'm not really sure.
No, that's absolutely fine. I mean, I'm not an expert in either of those aspects either, but in my career we had to advise customers on how to improve things, and you learn along the way. But no, I just wondered how far you're going. I know, for instance, the company I recently retired from, they've now changed their focus in the automotive sector towards EV bearings and other products, really, for the EV market, because that's where it's going. So I think bearings and the materials they're made of and the heat treatments, all those things will change as well as you go forward. And the lubricants to go alongside that as well. So I think the whole industry needs to move in unison.
I think I'm going to have to intervene because I think we're going to run out. Thank you so much for your question, Gerald, and hopefully we can pop you in touch with Alexander to continue offline. But as it is now 1 o'clock, I think I need to wrap up and say thank you once again, Alexander, for an absolutely fantastic presentation to us. Great webinar. Thank you. Our next webinar, we're taking a little break for Easter, and we'll be back on Friday the 30th of May for our next talk. I believe we've got Dr. Robert Elkington from the University of Leeds joining us next time. And I can also announce already, if you haven't already heard, we will have the 34th Mission of Tribology Research at One Bird Cage Walk on the 3rd of December this year, which I know is a long way away, but we do have abstracts open now if you would like to get ahead. Thank you very much. Have a great rest of your day.
Thank you.